Hi everyone, in this video we will see together how the reading principle with the NanoFrazor works. It's quite an interesting topic because it can generate also a lot of confusion, and it's good to understand first of all the difference between the most commonly used method of measuring the topography, which is the AFM topography method. It's important to understand that the NanoFrazor works in a different way. So the way we measure the topography is not the same way that an AFM tool measures the topography. That's the one first thing to keep in mind. And we will see practically how this works. First, I want to just quickly remind you a basic concept about the NanoFrazor technology, the closed loop lithography. So we saw together that with the NanoFrazor we can do patterning and imaging. We can also just do imaging, but when we usually use the NanoFrazor, we do lithography. So we import a layout here. It's a grayscale layout with different depths of pixels, and line by line we do a writing in the forward direction, and then in the backward direction we do an imaging of the topography. So as you see here, step 1 is patterning, step 2 is cooling, step 3 is imaging the topography, and then we can use a feedback algorithm. What's important to keep in mind is that when we do the patterning, the tip is hot because we use the heater, which is a resistor that we call writer, and this resistor is in the best position to heat up our tip. Well, when we do the imaging step, our tip is cold because we use another resistor, which we call reader, and this reader is farther away from the tip. So the tip is fundamentally not being heated up much during the process, and we can assume that it's a cold tip. So as you see here, this is what the NanoFrazor software output gives us, the live topography image. And by using this data, we can also use a feedback algorithm. So that said, let's also see some visualization of the position of the writer and the reader. Here you can see some SEMs and a TM of our cantilevers. So this is the structure of our MBS cantilevers. And we can see here, it's a picture where we apply a voltage on the resistor of the writer. And we can see that this basically generates a glowing effect around it, because of course if the temperature is high enough, then we start to see some glowing, and the higher the temperature, the stronger is going to be this glowing effect, as you may also imagine. And on the other side of the lever, we have our reader resistance. So you can also very well understand that if we heat up this resistor, then heat doesn't effectively flow well to the tip, and the tip is pretty much cold when we do this process. Moreover, it's important to mention that when we do the lithography step, so the writing step, the writer heater is usually used at 950 Celsius, can go up to 1400 Celsius, which is basically melting point of silicon, while the reader temperature when we do the imaging step is usually kept at 450, 500 Celsius. So it's also another thing that I want to communicate to you, so that you can even believe more the fact that the tip doesn't get hot when we do this process, because temperature is also much lower on the reader. So why it is important to understand this? It's important to understand this because when we measure the topography with a NanoFrazor, it's important to understand the heat exchange. So we use, first of all, this reader that we just saw here. It's a resistor. And what we can try to understand in order to have a better idea of how the reading works is heat flux, right? So what we know is that air is an insulator. So you can think that as we have more air between the resistor and the substrate, then the flow of heat is reduced and the temperature is higher with a same voltage applied through this resistor. And I also wrote here that this is true for both reader and writer, or for any sort of heater, right? If we increase the amount of insulator around it, then the temperature is going to be more concentrated because the heat flux is going to be reduced. So let's visualize this for the reader in two cases. In one case here on the left, we are, let's say, close to the surface, while in the other case we put the cantilever farther away from the surface. So in the first case, we have a distance reader surface which we call D0, and we apply a voltage on the reader which we call V0, and we have this certain heat flux, which also follows the topography, right? So if we are closer to the topography here, because we have, let's say, PPA or any solid material, the thermal conductivity of any solid material is much higher than air, so will act as a heat sink basically. In the second case, we have a larger distance between the reader and the surface, so the heat flux is going to be reduced because there is a lot of air around it. And this means that in the first case, because we have a greater heat flux, the reader temperature, if we apply the same voltage, will be the same. In the second case, if we apply the same voltage, the temperature on the reader will be higher. Right? So this is we already starting getting into the concept of temperature, heat flux, and voltage that we can apply on our reader. So then let's do another step. So how can we measure basically the topography? Here I put three cases. One case where we don't have a topography. Second case is where we have a step. And third case is where we have, let's say, a hole. The first case, we assume that we have this heat flux which is pretty much constant between the surface and the reader because there is no topography, and we keep always the same distance. So we have a certain reader temperature if we apply the same voltage. In the second case, we encounter a step going up, the topography. And in this case, this causes a bending of the cantilever, and this bending also increases the distance between the reader and the surface. So this causes a different heat flux from the reader to the sample, and specifically this heat flux is going to be reduced. So again, if we apply the same voltage, in this case we have a higher reader temperature. In the third case, and so we go into a hole, so the sharp tip is going to go into this hole like this, and because there is a geometrical distance between the reader and the tip, which we saw here, and this is also a mechanical limitation, right? The reader is always going to be pretty much in that position. Then the reader will result in a closer distance, between the surface. So D2 is going to be less than D0, the initial distance here. And in this case, if we apply the same voltage on the reader, V0, we will have a smaller temperature with respect to the first case. So in this sense, we're able to understand which kind of topography we have. And in general, we can say that the bending of the cantilever when encountering a topography in contact mode reading changes the distance between the reader and the substrate, thus modifying the heat flux between the reader and the sample. It's not just necessarily the bending, but also, as you can see in this case, when we go into a hole, it's also the geometrical distance between the reader and the tip that causes the distance between the reader and the surface to decrease. And one thing that I would like to mention and stress is that we always do our reading in contact mode, because in order to have a deflection, a mechanical deflection of our cantilever, we always need to be in contact. One other thing that I wanted to wrap up in this slide is maybe highlighting a little bit the differences between NanoFrazor and AFM in a very simple way, so that we're on the same page also after some things that I just mentioned to you. So let's start with the AFM because probably all of you know how the AFM works. In the AFM, we have a photo detector that measure the deflection of a laser that is shown onto the cantilever. And when the cantilever deflects because of topography, then this causes a deflection of the laser, and then we are able to measure the deflection of the cantilever through this photo detector with 4 quadrants. So in this way, we're able to measure the topography of our sample. And it's important to mention that the AFM works in contact, tapping, and non-contact modes. Then if we go to the NanoFrazor, in this case, the reader, which we saw here, uses the heat exchange between itself and the sample to image the topography by measuring its changing resistance. So let's assume, like in this case, for example, we have a sine wave on our substrate, and we assume that the heat flux should follow also this sine wave, right? But what we practically do is measuring the changing resistance of the reader by using the voltage that we apply across it, and measuring this changing resistance, we're able to image the topography. And this can be done only in contact mode. So I hope that this clears some doubts about the reading principle of the NanoFrazor, which is quite unique. And lastly, I want to mention a couple of things about thermal conductance correction, which are also mentioned in another video with a sort of a demonstration of how thermal conductance correction works. And I really suggest you to watch also that video to understand even better how the reading works with the NanoFrazor. What is a thermal conductance correction? Well, you may think that what I described to you, our reading principle, is great, but there are some flaws, right? If we have some materials or certain topographies, or if we have topographies of different materials with different thermal conductance, thermal conductivity with respect to the substrate, for example, this will generate a different heat flux because let's say if these triangles are made of platinum and the substrate is silicon dioxide, then they will act as a much say stronger heat sinks, and this can generate some artifacts, which in this case we can call ghost topography, because the distance between the tip and the reader is fixed. So when we go across these triangles with the reader, this will generate this ghost topography. So we may have problems when we have very different thermal conductivities or very sharp changes of topographies, very deep holes, very large topographies, because we change the heat exchange between the reader and the surface. So we have a way to solve this, which is called the thermal conductance correction. This is also better visualization of the problem. So in case we have, let's say, a step with two different materials, then what we measure with the NanoFrazor is a convoluted signal. So we measure the topography and also the thermal conductance. So the thermal conductance correction introduces another out-of-contact read step, which only measures the thermal conductance. And then we're able to subtract this signal from the convoluted signal and have a topography only signal. So this is kind of the working principle of this. And in general, we can have, as I was mentioning earlier, an increased flux of heat due to a closer topography or because of material changes. So it's a correction that often helps in having better imaging of our samples, and it may also answer some doubts that you may have. Okay, what happens if I have different materials, very different topographies in the area that I'm scanning? We have a solution for that. And again, I recommend you to watch the thermal conductance correction video to understand more and see how it works with the NanoFrazor. Regarding our reading process, I hope this helps you to understand how this works, and I will close the video now. Thanks for watching, and see you in the next videos.